Here's another example for matched pairs for means. A random sample of non-English majors at a selected college was used in a study to see if the student retained more from reading a 19th century novel or by watching it in DVD form. Each student was assigned one novel to read and a different one to watch, and then they were given a 100-point written quiz on each novel. The test results are shown. At alpha equals 0.05, can it be concluded that the book scores are higher than the DVD scores? We have 7 students here, and they're performing 2 different tasks, and we want to compare those tasks. So since we are comparing these 2 different outcomes, we're going to use matched pairs or dependent samples for means. So the first thing that we need to do is make sure that we are choosing the correct test. So this first page on the template is for independent means. We can see that down here, independent. I want to switch over to the dependent and put in this data that is provided here. And I will enter that data over here into sample 1 and sample 2. So I'll delete those out. So I'm going to enter the sample 1 will be the book data. And sample 2 will be the DVD data. And then over here in the difference column, this would be used for the confidence interval if we needed to do a confidence interval. I know this problem is doing a hypothesis test, but I'm going to show you the confidence interval on this problem as well, just so that you know how to do it. Now the first thing though, even though we have our data entered here, we kind of need to set up our hypothesis test. I have a tendency to go right away to the technology, and we need to write some stuff down. So in the hypothesis test for matched pairs, the assumptions that we need, the sample or samples are random. We have random sample of non-English majors. The sample data are dependent. Here we say that they are dependent because each pair is corresponding to one particular person. And so that one person and their knowledge from a book versus that one person's knowledge from a DVD, even though they're doing different books, it's coming from the same person. So we have a dependence relationship between the book scores and the DVD scores. And then when the sample size or sample sizes are less than 30, population or populations must be normally or approximately normally distributed. We're going to assume normality for the sake of this exercise. So if the population, if it's not clear whether the population is normal, because we're learning, we'll assume normality. If the population truly isn't normal, there are other tools that we can use for testing hypotheses, but those aren't covered in our class right now. So know that there are other tools out there that we can use if a population is not normal, but for the sake of practice and what we're doing here in our class, we're going to assume normality. Now we need to come up with our hypotheses. So we have a null hypothesis and an alternative hypothesis. We have scores for books. We don't have a proportion. We have means. So I'll have mu1 and mu2. Null hypothesis is always equal, and book is mu1 and DVT is mu2. Can it be concluded that the book scores are higher than the DVD scores? So higher means the book's mean would be larger than the DVD's mean. And we'll make this our claim. We have alpha's 0.05. I'm going to start out with my t-distribution here. Since I have a greater than, I'm going to have a right-tailed test with my rejection region to the right. And know that even though I have the template and I know the template tells me reject or do not reject, it's a really good practice to understand why by drawing out this graph, which is why I want to see your graphs. I want to see you make that connection between the greater than in the alternative, the right-tailed test in the picture, and then putting that test statistic in there or comparing that p-value to alpha. Even though the template does it, you need to disseminate that information and interpret it for me. Okay? And with all that, we have n. N is 7, so degrees of freedom will be 6. Remember, this one is n minus 1. So I've got my data in here. And I'm going to use the t-test in the analysis tool pack. So remember, if you're in Excel, you'll go to the Data tab, and Data Analysis will be on the far right. Since I'm in Google, I've got my analysis tool pack already loaded. If you don't know how to do that, I do have a video on showing you how to install the analysis tool packs on both Excel and Google. And here we have the analysis tool pack in Google. Recall that Excel pops up a window, but it's the same order. So the intention is that this Google Excel Minor Analysis Tool Pack is mirroring the Excel tool pack. And we're going to click down here for this t-test for paired to sample for means. Variable 1 range, we're going to click on sample 1 data. And I did that backwards. I keep forgetting this. For Google, I have to first select it and then click on my range. And then we'll click out of that. I'll select variable 2 range and I'll click, and then it changes. I have to get used to that because that's different for me. Hypothesized mean difference, we always use 0. I did not select the labels, so I'm not going to click on labels. Alpha is 0.05, so I will leave that there. And the output range, I'm just going to click on this first cell right here, E5, make sure that it changes, and OK. And when I click OK, it runs the test. There we go. And don't worry too much about the lines. I think it's overwriting what I had before when I worked this test previously, but that's okay. So we can see our means here, our variances for each of the variables. We have 7 observations, n is 7. We're going to skip down to this t statistic, 2.812. We have a p-value here, and the p-values for one tail, t-criticals for one tail, and then we have a p-value for 2 tails and a critical value for 2 tails. Notice that when I went to this analysis tool pack and I entered in my information, I did not tell the analysis tool pack which alternative hypothesis I had. So this generates both. If I had a not equal to, I would use the 2 tail, but since I have a greater than, I'm going to use the 1 tail. So I need this information right here. And that test statistic 2.812. So these 3 values right here are the important values that I need. So I'm going to first take the critical 1 tail value, 1.94. That's going to go here. I can take my test statistic 2.812. And I'm also going to write down my p-value, 0.0153. And we'll compare that p-value to alpha. So remember, we have 2 comparisons going on here, and they should lead us to the same result. Traditional method up top compares critical value to test statistic. Notice I have my rejection region marked off, and my test statistic is in the rejection region. So we would reject the null hypothesis. It does not seem that they are equal. If we're comparing the p-value to the alpha, I notice that second decimal place 1, second decimal place 5, my alpha is bigger. Since my p-value is smaller than alpha, again, reject the null. The idea here with that p-value is this is the probability that I select a sample from a population, from populations, where the means are equal. Since the p-value is really small, 0.01, I have a 1% chance of randomly selecting this particular data from 2 populations that are equal in mean, that have equal means. That p-value is too low, the probability is too low, so I would reject the null. It can't be the case that the means are the same, since the p-value is too low. Now, there's a tiny, tiny, tiny possibility, right? We're never 100% certain in statistics. There's still that tiny bit of chance, but there's enough evidence to support the claim that my means are different, particularly that the book scores are higher than the DVD scores. And so that's our conclusion. Now, suppose I want to create a confidence interval for the difference in the means. We'll pull up our template again to do this confidence interval, and this time it's a little bit different. Since I already have the data in here, I know I have another example where I'll do the confidence interval, but I wanted to walk you through how to do it for this particular problem. So if we were creating a confidence interval, the first thing that we would need to do is make sure we calculate the differences in the samples in the difference column. So what I'm going to do is type in equals, click on A2, minus, click on B2. So I have A2 minus B2. Google asks me if I want to autofill. Excel does not do this, so I'm not going to autofill so I can show you how you can get the rest of those differences fairly quickly in both technologies. So I click on the difference where I have my formula. I make sure that my mouse turns into the new plus sign, and I'm going to grab that square handle in the bottom right corner. Click and hold on the mouse, drag down all the way until the end of my data, and release. And doing that, I get my differences. Now, I'm going to scroll down. Let's take a look at what's down here. So, level of significance. Let's say we're going to do a 0.05 level of significance. Once I put in the differences and my level of significance, or confidence level, that should be confidence level. Okay, so once I have the differences in the difference column and I put in the confidence level as a decimal 0.95, I get my average, my mean, my standard deviation, the critical t-value for two tails, and this is coming from the fact that a confidence interval, we're looking on both sides of the mean. So we take that confidence level and divide it in half. Sample size is 7, and then we have our lower limit and our upper limit. What's important about this confidence interval is that I have 0.87 to 12.5. 0 is not in this interval. This is another example, another piece of evidence against this null hypothesis.